This is the second part of S2P2. Homeostasis is the maintenance of a constant internal environment. So we're going to talk about homeostasis. It was first brought to the scientific forefront by a French physiologist by the name of Claude Bernard. Basically, he said the consistency of the internal environment is a condition for free and independent life. He was kind of the first one to come up with the idea of homeostasis and provide some evidence. Perhaps the most influential person in the homeostatic field, though, is Walter Cannon. Cannon did a number of different things, including coining the term homeostasis. He meant it to mean staying within oneself. He also came up with the term fight or flight, which you might have heard in previous classes. And he also came up with 4 postulates. He did this, in the late 1800s, early 1900s, before we actually had evidence for all these postulates. And he said that the autonomic nervous system plays an important role in homeostasis, that systems are under what we call tonic control, that antagonistic controls are very important. It's the third time we've seen that term, antagonistic, different usage again in this section. And chemicals have different effects in different tissues. So those were his 4 postulates. Let's kind of look at it a little more detail. So the first postulate was the autonomic nervous system, or ANS, plays an important role. We can divide the autonomic nervous system up into 2 branches, the parasympathetic, which is sometimes known as the rest or digest or feed and breed, and the sympathetic, which is known as the fight or flight or fright or some sort of 8 word, right? And it works below the level of consciousness, both the sympathetic and parasympathetic. And so many of the things involved with homeostasis is done by these. You don't have to memorize these or anything, but just, kind of let you know that ANS plays an important role. Second idea was tonic activity. And one of the things about tonic activity, it's something that occurs that allow us to have a single controller. And the single controller is like a radio that's always on. You can turn it up, you can turn it down in terms of volume, but it's always going to be on. And the idea would be in some cases, like this example here with blood vessels, we have a constant signal going to blood vessels. And if I want to constrict a blood vessel, I can increase the frequency of that stimulation. If I want to cause dilation of that blood vessel, I can decrease the stimulation. But it never actually turns off. I can just increase or decrease it. I can't turn it off. And if it turned off, then you couldn't get any more larger degree of this case of a dilation if we turned it off. Because once it was off, you couldn't do any less than off, right? So tonic control helps to modulate activity when there's a single controller. We have tonic control in the endocrine system. As an example, we measure HCG, human chorionic gonadotropin, in pregnancy tests. And there's always some level of HCG in our blood. And in fact, men and women have levels of HCG. It just significantly tends to go up when someone's pregnant. There have been cases on record where, just in studies to check it, a few men have tested positive in terms of pregnancy tests because they have a high enough level of HCG. So, the idea would be we always have some level of hormones in our blood. It just doesn't have a high enough concentration to have a physiological effect. Another example that we see is sweat glands are exclusively under sympathetic control. And that gives us this tonic control. So at rest, we have a low heart rate, we have a low sweat rate, we have a low level of sympathetic activity. But during shock or arousal, we'll have a high heart rate, high sweat, and a high level of sympathetic activity. What this really means is the frequency of action potentials going to a sweat gland is significantly increased, and so sweat rate would go up. So, we can see that, and we can look at the idea of antagonistic control as well. So for our heart, and we looked at this in the biofeedback lab, right? If we increase sympathetic activity, we increase heart rate. And if we decrease sympathetic activity, we decrease heart rate. And that's through the sympathetic system. If we use the parasympathetic system, it's inversely proportional. If we increase parasympathetic, heart rate goes down. And if we decrease parasympathetic, heart rate goes up. And so I can change heart rate with these two antagonistic systems by increasing or decreasing one or the other. I can change heart rate. So that's a great example of antagonistic control. Blood glucose, right, is another good example. I can change the amount of insulin or glucagon in my bloodstream. Insulin promotes cellular uptake of glucose, and glucagon promotes the release of glucose back into the blood. And so they're antagonistic, right? They do the opposite things. The last idea is that chemicals can have different effects in different tissues. This is often due to what we call receptor isoforms. An isoform is a receptor that does the same thing but has a slightly different form or in a different tissue. So as an example, we have these isoforms of receptors that are called alpha, or sometimes known as alpha 1 receptors. And we see those on certain blood vessels. As a matter of fact, most of our systemic blood vessels have alpha 1 receptors. And when they get stimulated by epinephrine, adrenaline, right, it causes constriction. But on other blood vessels, like skeletal muscle, which really isn't a great example, heart's probably the best example, they have a different type of receptor for epinephrine. It's called a beta 2 receptor. And when epinephrine binds to a beta 2 receptor, this causes dilation. All right, so one receptor, same exact chemical, causes constriction. Another receptor, same exact chemical, causes dilation. And so this is an example of chemicals can have different effects in different tissues. So that's the 4 postulates for homeostasis that Cannon came up with. A couple other points about homeostatic control. Homeostasis helps to maintain our parameters near a set point. And the set point, let's say, is this red line here. That's the normal range of function. Okay? And it's controlled primarily through negative feedback. So if and this is temperature, so if temperature goes down, right, this has mechanisms to bring temperature back up. Temperature goes up, this has mechanisms to bring it back down. And we're always returning back towards the set point. That's called negative feedback. Negative feedback is irrespective of direction. So whether it goes down and back up or up and back down, that's still called negative feedback. Okay? If you stay within the desired range, there's nothing that needs to happen because you're in the desired range. And only when do you get out of the desired range, then do we start kicking on those negative feedback controls. Now, there are a couple different ways to maintain homeostasis. One is through local control. Sometimes that's called intrinsic or autoregulation. So local control, intrinsic, and autoregulation are all the same terms, basically. And what that does is it allows an organ or system to regulate themselves. So as an example, a blood vessel can cause, in periods of certain times of stress, can cause its own dilation to increase blood flow and oxygen levels through the blood vessel. Okay, and that is totally due to things within the blood vessel. So that's why it's called local autoregulation, because the blood vessel is regulating itself. If it doesn't happen intrinsically, it has to happen extrinsically. Extrinsically means it's from outside the system. And there's three types of extrinsic control typically. The first is neural, which is the nervous system. And again, according to one of Cannon's postulates, which makes sense, is that's due primarily to the autonomic nervous system, the ANS. And so whether it's the sympathetic or parasympathetic, right, that helps to control whatever variable we're talking about by the nervous system. The next one is called humoral. Humoral means it's carried in the blood. And so that's generally the endocrine system that's doing that. And since it's the endocrine system, it's primarily hormones that control that aspect of it. So that's our humoral portion. And then in some different systems, there's always an other that we have to worry about. And sometimes that's behavioral, or it could be other things as well that doesn't fit the neural or humoral categories at the beginning. So later on this semester, like for the control of blood pressure, we're going to look at how we control blood pressure from an intrinsic mechanism standpoint, from an extrinsic mechanism standpoint, and then break down the extrinsic into the neural, humoral, and other components. One of the things students don't understand is that set points are variable. It's, matter of fact, in my opinion, the worst named thing in physiology. And there's, two reasons for that. Set points is a compound word. It has two words, set and point, and neither one of them makes sense with the term. Set points can change all the time. The set point for your body temperature fluctuates throughout the day with what's called diurnal or day-night cycle, so diurnal variation. When you get a fever, what your body does is it resets the set point for body temperature to a higher level, and you fluctuate around that higher level. Okay. The other thing is set points aren't a point. It doesn't say, oh, we're going to keep the temperature at 37.2 degrees. It says, oh, we'll keep it somewhere between 36.7 and 37.7 or something. So it's a range of values that you can have in terms of the set point. So it's a terrible name because neither of the words within it hold true. All right, so set points change, and set points are not a point, but a range. When I was an undergraduate, I learned about this process. It's called feed-forward control. And I really, to be honest, didn't believe it. I always thought, well, I don't know what I'm doing 5 minutes from now. How does my body know? And how can it anticipate this change and start to increase these variables in a certain direction before things happen, before there's any stimulus, I guess is the best way to say it. So we're going to talk about the idea of what's called feed-forward control. Later on in my academic career, I had a class just on this process alone, and it convinced me that it does happen. There's plenty of evidence for it. But one of the things that helps regulate body temperature, and in part at least, are hormones. And the big hormone that really matters for body temperature is a hormone called cortisol. Cortisol does a number of different things, but one of them is it helps to regulate your temperature. And cortisol production is influenced by those circadian rhythms, those day-night or diurnal cycles. And what happens with some people is the plasma cortisol tends to go up before it becomes light. And so what it does is as you increase your plasma cortisol, the higher it is, the easier it is to deal with when you get up in the morning, and especially, in terms of your body temperature. So people that are said to be morning people actually have a feed-forward anticipatory effect of cortisol before they wake up. Other people, they don't start to increase their cortisol until they're physically up, and certainly the light plays a large role, but it allows them, the people that have the cortisol changes earlier, that feed-forward change allows them to function better early. Another good example of feed-forward control is when you get ready to exercise. If we were to measure your heart rate and respiration and things like that, especially if you're going to race, then you'd start to have these anticipatory changes in heart rate and respiration. Those would go up. And then the idea would be, so when you compete, you need to raise your heart rate, you need to raise your respiration. Well, if it's already started going up, it's easier to get to the point where you need it earlier and compete better. So feed-forward control anticipates changes and starts to change the variable in that direction before there's any real stimulus. Even salivation is an anticipatory reflex. As an example, Pavlovs Dog, and you probably understand that experiment where you ring a bell, you feed the dog, and the dog starts to salivate. And then at some point in time, when you just start ringing the bell, the salivation starts even before the food is there because of that anticipatory reflex. Speaking of reflexes, one of my pet peeves is the idea of reflexes. We're going to do a lab on reflexes probably, but I don't think we really identify reflexes very well. I have a few anatomy books in my office, and I looked recently at one just to see what I was talking about. And it basically said a reflex is an involuntary response. And I looked at another book, and it basically said the same thing. And one of the problems with the way reflexes are typically defined, especially in the non-physiology books, is they don't do an adequate job in terms of explaining what it really is. And so you can put these 5 things together into a sentence if you want to make a definition. But here are the things that make up a reflex. Here are the characteristics of a reflex. So first, like the definition mentioned, it's an involuntary thing. Okay, there's no conscious control of it. You can't start it. You can't do anything to prevent it. It's involuntary. Okay, so there's no conscious control. It works below the level of consciousness. So to have a reflex, you need something that's involuntary. Second thing is you need what's called an adequate stimulus. An adequate stimulus is the stimulus that excites a receptor. And as an example, light excites receptors in your eye so you can see. Don't do this, but if you took your thumb and pushed it really hard into your eye, you would see stars, you would see flashes of light. Okay, so you are stimulating receptors, but it's not the way the receptor is supposed to be stimulated, so that's not an adequate stimulus. Okay, so you need adequate stimulus. The third thing is, and I kind of mentioned this already, since you have an adequate stimulus, you need a receptor. Okay, so you have to have a specific receptor to receive that stimulus. Okay, so that's number 3. Number 4, you need to have what's called a patterned, or some people call it stereotyped response. Okay, so pattern means you get the same result every time. So it's not like a cartoon when the cartoon character goes to the doctor and the doctor does a little knee-jerk reflex like in that picture, and the other leg kicks out, and then they do it again and the other arm moves, right? It's going to follow the exact same neural pathways every time. That's what pattern means. And then the last one is graded. We've seen graded a couple times. Graded means the size of the stimulus determines the size of the response. So if you tap lightly, you'll get a small response because of the small stimulus. And if you, in case of knee jerk, if you hit it a lot harder, you'll get a larger response because of a larger reflex. So, you can put these things together and, say, okay, it's, involuntary pattern graded response to an adequate stimulus at a specific receptor. I mean, that could be a putting those things together, talk about a reflex. But I just think that the first definition is inadequate. As an example, just going with an involuntary response. I was cleaning my front yard the other day, and I don't usually do that. I actually, because I'm lazy, pay a gardener to do it for me. But we needed something done at the time. And so I went out and raked leaves, which I don't usually do. And so I actually got a blister on my thumb. It was an involuntary response. I didn't want to get the blister. Is that a reflex? Well, no, because it doesn't fit the criteria, right? Did it have an adequate stimulus? Well, not really. It had a stimulus, the handle of the rake moving across my skin, but there is no blister receptor, right? So we don't have a specific receptor to have an adequate stimulus to, so the definition falls apart there. So getting a blister from raking would not be considered a reflex. However, as you see in this picture, the knee jerk, right, or patellar tendon, patellar ligament, whatever you want to call it, reflex would be an adequate stimulus. So the tapping on that would be an adequate stimulus to get a reflex. Now, if you have a reflex, all reflexes follow what's called a reflex arc. To have a reflex arc, right, you need 5 different things. We're going to look at the anatomical things responsible for that response. Okay. The stimulus and the response are not part of it. So notice, even though bottom left is stimulus and bottom right is response, they are not numbered. So they're not considered part of the reflex arc. Okay. First thing is you need a receptor. That's number 1. Number 2 is you need a sensory or afferent fiber to carry that information from the receptor to the integrator. The integrator is almost always the CNS, and typically the brain or the spinal cord for us. Okay. That's number 3. Number 4 would be the motor or efferent fiber. That's leading from the integrator, right, out, and that goes to the effector. That's number 5. And then number 5, right, is the last one, and that will carry out the response. So the 5 portions of the reflex arc: receptor, sensory fiber, integrator, motor fiber, effector. So here's an example of a fairly simple reflex arc, and we'll kind of look at it. So this is an example of the knee jerk, or sometimes called the patellar tendon or patellar ligament reflex. And what happens is you take the reflex hammer and you strike the tendon. That stretches the muscle. And when it stretches the muscle, it excites special receptors in the muscle, these little blue ones wrapped around the muscle here, okay, that are called stretch receptors. So there's our receptors. This is our afferent fiber. This is our sensory fiber that goes up to the spinal cord, right, and synapses directly on a motor neuron. Okay, so my afferent fiber is in blue. My integrator is the ventral great horn of the spinal cord. That's right here, where the blue synaptic end bulb, right, synapses on the cell body of the red motor neuron. That excites the motor neuron. So that goes my efferent fiber out the spinal cord to the muscle, and then in the muscle it causes it to contract and give my foot swing. So my efferent is the motor fiber, and then my effector is skeletal muscle. Okay, so just really quick, the stretch receptor, my afferent is the blue, my integrator is the spinal cord where the blue and the red meet, my red is the motor fiber, and my effector is the muscle. So that's 1, 2, 3, 4, 5 reflexes, 5 components of the reflex arc. So that kind of finishes the homeostasis chapter, and we'll pick up with the next set soon.